Okay, so welcome to Ordinary Level Electrochemistry. It is our last topic, so congratulations on getting through the course. Now I've asked you to do some revision exercises before we started, so we'll go through them very quickly. So all of the positive ions will all keep their own name, so sodium, potassium, silver, ammonium, calcium, magnesium, lead, zinc, copper. We then have two versions of iron, so they're called iron 2 and iron 3, and that goes on the basis of their charge. And the reason they get the Roman numeral numbers is because they are transition metals. And then we have aluminium Al3. In terms of our negative ions then, the name just changes for an element from chlorine to chloride. So then we have bromide and iodide. Nitrate, NO3- is a complex ion. Hydroxide, OH- is a complex ion, as is hydrogen carbonate and carbonate. Sulfide comes from sulfur, so that's just a changing of the element name. And then we have sulfate, SO4 2-. Now you have done your Microsoft Forms quiz, and I will post the scores when I get a chance to go through them. So here you just have to decide what is oxidized and what's reduced. So we write down the numbers of the ions plus 2. So here, if you remember oil rig, oxidation is loss, reduction is gain. And we also have my silly letters OIR and RDL. So OIR, oxidation, is an increase in oxidation number. You don't really need the OR part because you don't have to write half equations. Woohoo! But you do need to know that oxidation is an increase in oxidation number. So here, this is what is oxidized, and plus 4 to minus 2 is a decrease in oxidation number. So this is going to be reduced. Here it is a plus 2. This is an element. It has no charge. It's a 0. This is also an element. It is 0. This is plus 3. So in this one, it is iron is the thing that is oxidized, and mercury is the thing that is reduced because it is a decrease in oxidation number. So here we have a 0, a 0. This will be minus 1 because it's chlorine. There are 3 of them. Makes it minus 3, which must make the astatine positive 3. So in this case, this is reduced. Chlorine is going from 0 to minus 1, and astatine is going from 0 to plus 3, so that is oxidized. Now we have also, or you will have to decide what is the oxidizing agent and what is the reducing agent. So oxidizing agents, we have said, are themselves reduced, so you're just looking for the thing that is reduced. So this is the oxidizing agent, this is the oxidizing agent, and this is the oxidizing agent. So I've colored those in blue, and obviously you would color them in, and you would put a label down, and you would just write oxidizing agent for your examiner. Okay, change our color pen. So then reducing agent is itself oxidized, it's opposite world. So we now find the thing that is oxidized. So it's the chromium in the first equation, it is the iron in the second, and it is the astatine in the third. And for each of these, you are going to write next to it reducing agent because you are brilliant. Okay, so that was just a little reminder of ionic compounds and what it is they do. I've already given you the notes as they match the pink book. In the table that you will see, there's extra things in there. It is only these 3 experiments that you need to be able to describe for ordinary level. So I'm going to change my share.
Electrolysis is electrical current flow through a liquid which causes chemical changes. Yes, you did hear that correctly. Current flowing through a liquid. Now, not all liquids can conduct. The liquid can be a molten ionic compound or an aqueous solution. In either case, it must be able to carry current. Let's take a common example, table salt. If you heat sodium chloride to over 801 degrees Celsius, it will melt. The liquid will contain free-flowing positive sodium ions and negative chloride ions. This simply means that sodium and chloride ions are free to move within the liquid sodium chloride. Positive ions are called cations. Negative ions are called anions. Now consider putting two electrical conductors into the liquid. Copper would be good as it has a higher melting point. Nothing happens to the ions at this point, but if we connect the two bits of copper to an electrical cell or power supply, then things start to get interesting. We do need to sidestep for a moment to look at electrical current in a metal. From our lesson Behaviour of Metallic Structures, we know that electrons in a metal aren't bound to particular atoms. They form a sea of electrons that can move easily if a potential difference or a voltage is applied across it. This could be from an electrical cell or a battery. The electrons will begin to drift towards the positive terminal of the battery, and this is what happens when current flows. Current is the movement of charge, in this case, electrons. Now, let's go back to our molten sodium chloride. We've added our copper wires, let's call them electrodes, and now we'll connect these to an electrical cell. The electrons will start to flow in the wires, and this will cause one electrode to become positively charged and the other negatively charged. This has an immediate knock-on effect in the molten sodium chloride, which you'll remember is a mixture of sodium cations and chloride anions. Anything positively charged in the liquid, in this case the sodium ions, is going to be attracted to the negative electrode. And anything negatively charged, in this case the chloride ions, is going to be attracted to the positive electrode. This is because opposite electrical charges attract. When the ions meet the electrodes, electron exchange happens, and this triggers a chemical reaction. Solids can form, gases can be given off, and new solutions can be left behind. It all depends on the liquid and what material the electrodes are made from. There is more detail about this process in our lesson Interpreting Electrode Equations. There are special names for the electrodes, which are usually metal plates with a larger surface area than a piece of wire. The positive electrode is called the anode, it attracts anions, and the negative electrode is called the cathode, it attracts cations. The liquid is effectively conducting electrical current. The only difference is that the charge carriers in the liquid, in other words the charged particles that are moving, are ions. If a liquid has free-moving ions and can conduct like this, it is called an electrolyte. Remember that electrolysis can also take place in ionic solutions as well as molten compounds. The more concentrated that solution, the greater the ion flow rate. Ion flow rate can also be increased by increasing the potential difference or voltage across the cell. We'll be studying several examples of electrolysis in more detail in other lessons. For the time being, though, here is a summary of the key ideas about electrolysis. Electrolysis is the flow of electrical current in a conducting solution or molten liquid that causes chemical changes. The conducting liquid is called an electrolyte and has free-moving ions. The conducting plates, bars or wires inserted into an electrolyte are called electrodes. Positive ions are called cations and are attracted to the cathode. Negative ions are called anions and are attracted to the anode. When current flows in an electrolyte, it is the ions that move and carry the electrical charge. When current flows in the electrodes and wires, it is the electrons that move and carry the electrical charge.
Okay, so that is a really good introduction. I really like that video. So we are going today to talk a little bit about the language that goes with electrochemistry as well as the reactions that you need to know about. So just to recap, electrolysis is when you use electricity to bring about a chemical reaction. And we have it's really important that, and this we've learned this when we did ionic compounds, they can only conduct electricity when they're molten or when they are aqueous, so that's salt dissolved in water. And there's loads of commercial uses for it, so things like purifying copper and electroplating, which we'll talk about. So we have our definition now, and here is just some words that may become important. So electrolyte is the substance which electrical current is passed through. So this is your molten salt, or this is your salty water. It's one of those two things. Next we have the electrodes, and they are the rods that come in contact with your electrolyte, and we have these two words down here to describe what they are. So you're either inert, which means you are unreactive, so this is how we describe group 8 in our periodic table. All those noble gases, they are inert, but in terms of electrodes, they will be able to carry current, and they are usually platinum or graphite carbon. If you have an active electrode, then this is actually taking part in the experiment, and that has a consequence. We then have spectator ions, and these are ions that are present but they are not involved in the chemical reaction. Now I use panic to work out what my anode and cathode are. So the P is positive, the A is anode, the negative, and C for cathode. And we also then have another little new sentence. We have anox and we have red cat. And anox stands for the anode undergoes oxidation, and red cat is for reduction. Now in a circuit diagram, when you see it, they don't always put in the charges here, but they will always have something drawn like this. So this is your cell or your battery or your power pack, and the bigger line is always the positive anode and the smaller line is the cathode, so you can get the idea which way electricity is going to move. Okay, so it's always the big line, and the anode attracts anions, so it must mean anions are negative, and the cathode attracts cations, and the must mean cations are positive. So way back in Form 4, we drew this fabulous picture of a cat, because you know I'm so great at quality diagrams, and we gave him a little positive face and positive smile, so he was a posi cat, so cations are positive. And we also drew an ant. He was again another quality diagram from me. He looked like this, but he was all negative. I have no idea how many legs ants have, but he was all negatives in there. So we had a posi cat and an ant, and the anion are negative, cations are positive. Now you have this diagram in your book, and I've already labeled it up for you. So this is our positive, our anode, this is our cathode, that is negative, and we've said oxidation is going to happen here because it's anox, and reduction is going to happen here. And then we go back to oxidation is going to be loss of electrons, and reduction is going to be gain of electrons. Okay, so, and it's the electrolyte is completing the circuit for whatever to describe it. So for electricity to flow, you have to have a complete circuit, because electricity can't jump. In this diagram on the right, we have a bulb that lights, so that's telling you your electrons are going to flow. Now, in terms of the three little experiments, this is of the three, this is the only one that they've asked, and they've only ever asked it in terms of the products. They haven't asked you about what's oxidized and what's reduced, but it is on the specification. So for you, what's going to be important is really your anode and your cathode observations. What is it that you are seeing at the anode and the cathode? So the first experiment that we look at is just to show ions, how they move in an electric field, because that's a really difficult thing to visualize. Now, I can't show you this because we are not allowed to play with the copper chromate anymore in schools. So what they've done here is they have taken some filter paper and they have put copper chromate on, let me get rid of their sound. They have put copper chromate in the middle, and then they apply current to the filter paper, and you will see that the negative chromate goes toward the positive anode and the blue copper goes toward the negative cathode. So this is as good as I can do for you, and this would be what we would see if we were in school, because we can't actually do it in person. So we're looking, the fact that the ions are coloured allows us to see what's happening. So your copper chromate is green in the middle, and once you apply your charge, positively charged ions will go toward the anode, and the negatively charged ions will go toward the cathode. Okay, so for you really it's just what is the observation. So the positive electrode, the anode attracts anions, which is the chromate, it goes yellow, and the cathode will attract the positive cations and it will go blue. And there are spectator ions in there, they don't do anything for us. So it's the observations that are important for you. In this one then, slightly more complicated in its setup.
Electrolytic refining of copper. Electrolytic refining is a process of obtaining pure metal by the process.
Okay, I'm going to leave him do his little spiel. So our setup for this is ever so slightly different in that we now are going to use copper electrodes, and we are going to put it into acidified copper sulfate. I presume this is playing for us. We get it up to here. So you have, it doesn't actually matter if you have a pure or impure proper or electrodes here. So when we do it in school, we use 2 copper pieces, and what we find is that as you run your electrolytic cell, your anode actually decreases in size and your cathode actually gets bigger in size. And what's happening here is the copper is being oxidized, it's losing electrons, it's making copper ions, and they end up coming over to this side and gaining those electrons back again. At the bottom here you can see some sludge. I'm going to go back to him. You can see sludge forming, and that's other impurities that are not copper. And that would even happen for us in our lesson. We get a tiny little bit of sludge, nowhere near as much as of this. So obviously this has applications in purification of methods, and it has applications if you wanted to plate something in copper, like a spoon or a coin. Even I do it with coins, just to show you that you can change the color of them and plate them with the copper. Now, as I say, for you it's going to be what are the observations. So our electrodes are copper, and they're active electrodes now because they're actively taking part. Our electrolyte is copper sulfate, and that's just to keep supply of copper going. And what we notice is that our cathode actually gains mass, it gets bigger, and that's because it's pure copper is being attached, and our anode loses mass. So there are your 2 observations. So copper from anode loses mass, and the cathode is going to gain mass. You don't need the half equations, I thought I'd taken them out. And you will get your impurities in your sludge underneath. Okay, so if you can think about it in terms of the reaction, copper is losing electrons, so that is where the OIR, it's an increase in oxidation number, and electrons go on the right hand side. So it's losing these 2 electrons. The copper ions then are attracted to your cathode, and they gain their electrons again, and they are put on as pure copper. So this is going to get bigger. Then in our last one, it's one we did when you were in junior cycle.
Salt water, a transparent bowl, 2 glass test tubes, a 4.5 volt battery, 2 twin wires with alligator clips, colored plasticine, 2 pencil leads. Connect 1 pencil lead to the wire by means of the alligator clip. Then seal the connection with plasticine. Repeat this procedure with the other lead. Fill the test tube with water and insert the pencil leads in them. Be careful not to let air bubbles into the test tubes. Attach the free terminals of the wire to the battery. Do not forget which clip you have connected to the positive pole, that is shorter, and which to the negative one. After a few minutes, you will notice that small air bubbles have developed on the surface of the leads. After 3 hours, there is a lot of gas in the test tubes. However, in the test tube connected to the negative pole, there is double the amount of gas respect to the other. Why? Electricity breaks down water molecules, freeing the oxygen and the hydrogen that compose it. Hydrogen gas, H2, forms around the negative lead, while oxygen gas, O2, forms around the positive one. Every 2 water molecules broken down by electricity form 2 hydrogen gas molecules and only 1 of oxygen gas. For this reason, one test tube has double the amount of gas respect to the other.
Okay, so this, as you say, is the exact same for junior cycle. She used carbon. I have real expensive platinum, or should I say Mr. Duncan has real expensive platinum electrodes that we can use. So she used salt water, but we would use water that has a little bit of sulfuric acid added, and that just helps the conductivity. So in this reaction, the sulfate or the spectator ions, they need a whole lot more energy to be able to get involved in electrolysis. And you just have to remember that at the anode you make oxygen and at the cathode you make hydrogen. The way I do it in my head is which one is which. Well, having oxygen is a real positive thing because we die without it. So therefore oxygen is made at the positive electrode, and then that must mean hydrogen is made at the cathode, at the negative. So that brings to an end the 3 experiments. They have asked this question for you at Leaving Cert Ordinary level, and of those 3 experiments, this is the only one. So electroplating. Electroplating is when you put a layer of metal onto the surface of another metal. I'm not going to show you that. And you essentially cover your cathode in the metal. So copper, by making it in cathode in copper sulfate solution, we just did that one earlier. You can also do it where you plate cutlery. So you would put a spoon made out of cheap metal or a fork at your cathode, and you would have the metal that you want to plate as your anode. So they do copper plating of cutlery, but my sister, bless her, got actually gold plated cutlery when she got married, and they just make sure the electrolyte is right, and eventually you would have lovely gold coloured cutlery over here because it would plate. So you'd use a copper anode and a nickel spoon at your cathode, and you'd use the correct electrolyte, so it would be something that would have the ions of interest in it. And just as far as you're concerned, the anode will lose mass because the copper ions are produced. If there's any impurities there, they'll fall to the bottom, and in your cathode will gain mass as your pure copper is deposited on it, and it is very, very pure. So just one other is silver plating. So again, silver anode, nickel spoon at your cathode. You'd have silver nitrate as your electrolyte, and again your silver ions are formed at your anode, and then pure silver is formed at the cathode, and that's where the plating comes from. So there's loads of different applications, a whole load of things. So you can chromium plate steel for your bathrooms, where all of the steel then is beautiful and shiny and will last for a while. So the last little bit we're going to do is a thing called the electrochemical series. We did it way back in Form 5 when we talked about redox reactions. And again, all it is a list of metals, and which one is the best at being oxidized versus which is being best at reduced. So it's potassium is your best, platinum is your worst. And if you live at the top, you are really easy to oxidize, so you're really ridiculously reactive. If you live at the bottom, you are the least reactive, but you're brilliant at reduction. So things at the top, easiest to oxidize. They obviously make the best reducing agents, and if you live at the bottom, you're easiest to reduce and you make the best oxidizing agent. So I gave you this silly sentence to remember it. Please come stay my Aunt Catherine's in the lighthouse because she's got piles. Because sometimes they can ask you which thing is more reactive, so it may help. Now, in terms of electrochemical series, it's just a list of elements in their order to be oxidized, and we see this, and you will see this, and loads of your questions will be on displacement reactions. So displacement reaction is when a more reactive metal takes the place of metal ions in solution, and there's nearly always going to be a color change involved, not exclusively but nearly always. So this is an example, and this is a use. They use scrap iron to displace expensive copper from solutions of its ions, like so. So just to do this is the thing that is going to be oxidized. This is the thing that's going to be reduced in our reactions. And yeah, so we will get ions produced at the anode, and we will get pure copper produced at your cathode. And we've said the iron loses electrons because it's oxidized, and the copper gains them because it's reduced. And we've said there's always going to be a color change involved, and this is the color change. So this is our iron at the beginning. This is our copper sulfate. Because iron is more reactive, if it wasn't a more reactive metal, nothing would happen. But because it's more reactive, it is going to form ions in solution, and the copper that's in here is actually going to come out of solution as copper metal, because these are copper ions in here, Cu2 plus and SO4 2 minus. So they literally do a swap, and here's the after. So now our iron metal is now copper colored, because this is now Cu, and in here now we have Fe2 plus and we have SO4 2 minus. So one thing oxidized loses electrons, becomes an ion, because this was the more reactive metal, and the copper ions that are in solution gain electrons because they're reduced, and they come out of solution, and you usually see them as the color of the metal. So have a look at the questions that are in class notebook now. It's just a few selection in there for you to try that are more like the questions that you get asked. And if you have any questions, come and ask.